All right, folks, happy Wednesday. We're going to go ahead and get started here. So we have two sections to cover today. They kind of go hand in hand, so I think it makes for a nice flow for the day. I do want to say that the content that we're learning today is really a preview, not for Calc 3. So all of the stuff we've done so far has really been preparing you for Calc 3. The stuff we're going to learn today is really in preparation for differential equations. Okay, so some of you might not have to take that, some of you might, but today is meant to serve as an introduction to what you would encounter in differential equations. All right. So with that, we're going to go ahead and get started. So we're going to start with 19.1, which is an introduction to differential equations. And then we're going to finish up today with 7.6, which is laws of growth and decay. All right.
Excuse me, Professor. I don't see the 19.1 notes on Canvas.
What's that?
I don't see the 19.1 notes on Canvas.
Are they not up there?
Nope.
I
All right. So let's go ahead and get started. All right, so 19.1 is an introduction to differential equations, all right? There are full courses on differential equations. It's actually one of my favorite courses to take, or that I have taken. I think that one of the things that folks who tend to enjoy differential equations, if you have a pretty strong algebra foundation, then I think differential equations is pretty fun. If the algebra is not as strong, then I think differential equations is a lot less fun. Okay, but the good news is if you felt really strong in like chapter 9, like the stuff we did at the very beginning of the summer, then differential equations as a course tends to be much more similar to Calc 2 than maybe anything you're going to take between now and differential equations, right? So let's start with what we know. So we know that derivatives, we can find derivatives in a lot of different ways. We learned a bunch of methods in Calc 1. Well, you folks did. You learned the power rule, right? That was a pretty foundational one. You learned the chain rule, which we've used quite a bit in this class. We've learned the product rule as well as the quotient rule. Okay, remembering that when we see two functions that are multiplied or divided, we can't just take the derivative of each part, but we need to, in fact, apply a specific rule, okay? Implicit differentiation, where we don't necessarily have to solve for y before we solve for our derivative, but we can actually just kind of take the derivative right away and then solve for my dy dx later, okay? I would say that these rules are pretty foundational for derivatives. And then when we look at integrals, we actually have a few more rules, right? We have learned the power rule. So that is definitely as foundational for integrals as it is for derivatives. We've learned U sub. And I feel like U sub is one of those things that when you first learn it in Calc 1, you're like, wow, this is so hard. And then now, you know, one course later, you're like, I really hope it's a U sub. It's going to be so simple. And so it's definitely a change in perspective there. But other techniques that we've learned, like integration by parts, partial fractions, trig subs, you folks know so many different rules now for both derivatives and integrals, all right? And I think it's important to kind of stop for a moment and think about all that you've learned. And then what's new? Differential equations, you basically spend an entire course learning about how to solve a very special type of equation called a differential equation. And so when you get to that course, if that is in your future, you're going to learn a lot of techniques, just like we have techniques for derivatives and just like we have techniques for integrals. Here are a few of the techniques that you tend to learn right at the beginning. So there's something called separable differential equations. We're actually going to learn that today. All right, that's one of the most basic types of differential equations. So we can think about that kind of on the same level as like power rule. There's a type of differential equation called a linear differential equation, and you're going to learn about what that looks like and what techniques you can use to solve that. There are exact differential equations. You're going to learn different techniques for that. And then you're going to use a bunch of substitutions, and you'll learn different techniques for that. Now, if you plan to move forward to differential equations, I would really encourage you to think, as you learn all the different techniques, how do you know when to use what? All right? So a big question to keep in mind is, how do I know when to use what? Okay. And I think that decision-making lens is really what sets folks apart in differential equations in terms of being successful, all right? So knowing, how do you know when to use which one? Now, this is all for the future, but today we're going to learn, again, about separable differential equations, okay? All right, so what is a differential equation? So a differential equation is nothing more than an equation that contains derivatives. So it might contain one derivative, it might contain two derivatives, it might contain three derivatives. There's a bunch of different kinds, but as long as it contains a derivative, it is considered a differential equation, okay? Now, it might include first derivatives. It might include first and second derivatives. It might even include first, second, and third derivatives. So there's a lot of different types of differential equations out there, okay? Now, differential equations are particularly useful because they allow us to model a lot of different real life scenarios. Okay, and so we're really getting to the point where it's no longer like in elementary school when your teacher was like, okay, well, we're going to use equations to find out, like, you know, if you have 5 cookies and you want to split them up amongst your friends, like that's one valid use of math. But I think what we're getting into is math that is perhaps a little bit more complicated and maybe a little bit more geared towards whatever your profession might be. And so a few of these uses include helping model population, okay, looking at falling objects, solution mixtures and equilibrium points, so thinking about chemistry, mechanical vibrations and heat equations. All of these include differential equations, okay? Now, we're only going to be looking at a very specific type of differential equation today. All right, we're going to be talking about the separable differential equation. Hang on. All right, there we go. So we're only going to be looking at the separable differential equation, and we're only going to look at applications where we're looking at a separable differential equation, okay? So specifically, a first order differential equation of this form, okay? dy dx, so there's our derivative, that's how we know that it's a differential equation, equals some function of x, so that's our g of x, okay? And some function of y, that's our h of y. Now, in this form, it is considered to be separable or to have separable variables because I can gather all of my y's on one side and all of my x's on the other side, okay? So if I look at this general form, how would I get all of the x's on one side and all of the y's on the other side?
Divided by one of them to both sides.
Yeah, divide by what?
By one of the equations to both sides, either g of x or h of y.
Okay, I need you to be more specific, or I need someone to help you be more specific here. I want to get all the x's on one side and all the y's on the other side.
Wouldn't you just multiply dx on both sides so that you get the dx on the other side, and then you divide h of the y function so that it's on the other side with dy?
Okay, so I heard you say you're going to take this dx and you're going to multiply it to the other side. Yeah.
Yep.
Okay, so that for some folks is a little bit of a weird thing, because I think when we look at dy dx, we sometimes forget it's actually a fraction, and so we can do that absolutely, like Dean said, we can multiply that dx to one side, and then I need to get that h of y away, so we're going to take dy, we're going to divide it by h of y, and now we've got all our x's on one side and all of our y's on the other side, okay? So when we think about separable differential equations, which are the kind that we're going to be working with, every case that we're going to see, it will be possible to get all of the x dx's on one side and all of the y dy's on the other side. There are some equations where that's not possible. Okay, but knowing that this is one of the most foundational ones, it should be one of the first strategies that you kind of try if and when you get to differential equations. Kind of like trying U sub or chain rule first sometimes makes your life easier, okay? So I just put a couple examples of separable ODE versus non-separable ODE. And ODE stands for ordinary differential equations, okay? So ODE stands for ordinary differential equations. So the separable type, if I look at this first one, dy dx equals y squared times x, I could use exactly what Dean said in this case. I could multiply the dx to one side, and then I would divide that y squared to the other side. And so this one, if I separated it, would look like dy over y squared equals x dx. Okay. What would this second one look like if we separated that differential equation?
dy
over sine of y
Over sine y equals?
ln of x times dx.
Okay. Now, these are some of the more basic ones, and I think those don't necessarily need a lot of introduction, okay? So we're going to do some of these, but we're also going to take it up a notch where we're looking at maybe we need to manipulate some things first before we can divide and get all the x dx and all the y dy's on one side, okay? Now, let's take a look at some non-separable ones, though, because as important as it is to say, here's a technique, this works in these cases, I think it's important for us to look at cases where it's not going to work and think about why it's not going to work, okay? So in this first one over here, dy dx equals y plus sine x, okay? If we employ the same strategy that we've tried for all the other problems so far, we would get dy equals y plus sine x dx. And what I end up with is y's and dx's being mixed together, okay? because the way this works, it works just like algebra. I would have to distribute this dx to both the y and the sine x. I can't just subtract the y away without multiplying it by the dx first, okay? So for that reason, it is non-separable. So the techniques we're about to learn will not work for this question, okay? Similarly, for this second one here, if I multiply dx to both sides, I have to distribute the dx to the 4x, the 5y, and the 4. And so when I distribute those, I'm mixing y's and dx's. And so this mixing of this y and that dx means it's not separable. Okay. The reason I wanted to point that out is because sometimes folks say, oh, separable differential equations are only when you're multiplying things. And if you're adding and subtracting, then you can't separate it. But we're actually going to look at a few cases where we'll learn some strategies on trying to separate it, even if there are plus and minus signs in there. Okay. So are there any questions so far? All right. So let's jump into some practice. All right. So we have about 7 examples today. Some of them are a little bit more basic and some of them are a little bit more what I call next level, okay? But again, all of this is to just kind of give you a flavor of what differential equations is like, okay? All right, so let's take a look at example number 1. Now we know that our goal is to try and separate them, meaning we want to get all the x dx's on one side and all of the y dy's on the other side. Okay, so in this case, what I'm going to do is I'm actually going to take this y dx and I'm going to add it to the other side. So that will give me 1 plus x dy equals y dx. All right. Now, I think this looks a little bit more like the examples we saw earlier. So I'm going to go ahead and divide the 1 plus x. What else should I divide by?
Y.
Exactly. We're going to divide by the 1 plus x and the y. And so some people like to do it in 2 steps. Some people like to do it in the same step. I'll leave that up to you, but whatever you do to one side, you have to do to the other, right? That's how equations work. So I'm going to divide by 1 plus x, and I'm going to divide by y at the same time. And if I do that on the left-hand side, I have to do that on the right-hand side. And what that gives us is this 1 plus x and this 1 plus x, those reduce to 1. So I've gotten rid of the x's on the left-hand side. And similarly, on the right-hand side, this y in the numerator and this y in the denominator, those also reduce to 1. And so what we have is dy over y equals dx over 1 plus x. Okay. So this is the stage that I usually call separated, okay? So we separated our equation, meaning that all of our y's and x's are on different sides of the equation. Now, after we separate, then what we're going to do is we're going to integrate, all right? That's how we get rid of our dy's and our dx's. And so I'm going to write this as the integral of 1 over y dy. Okay, that's really what it's saying. And similarly, on the right-hand side, I'm going to write that as the integral of 1 over 1 plus x dx. Okay. I think these are both things that we can integrate, right? The left-hand side is very straightforward. It is the natural log of the absolute value of y, okay? And that's going to equal, plus c is going to equal the natural log of 1 plus x, because I had to do a u sub, but the coefficient of x is 1, so it didn't actually introduce a new coefficient into my solution. So natural log of 1 plus x plus c. All right, so that is our next step. So after we separate, then we integrate. Okay. Now, this next part is, I think, a little weird for us. I think up until now, we've been very picky about anytime you integrate, if there are no bounds, you need a plus c. And that c represents a specific number depending on sort of initial conditions of a problem, okay? Now, the c on the left-hand side is a number, and the c on the right-hand side is also a number. They may be the same, but more than likely they're different, okay? But what happens in terms of solving a differential equation is that I heard this phrase one time and I thought it was a little, it didn't really make sense to me at the time, but basically we're gonna play fast and loose with our constants. Meaning we're gonna go ahead and just say, I know the c on the left-hand side is a constant and the one on the right-hand side is a constant. So I'm just gonna combine them and they're just gonna be on the side with the x's. So more often than not, when you see solutions for differential equations, it's gonna look more like natural log of y equals natural log of x of 1 plus x plus c. Like there's only one constant, okay? It's not that the first c was not important. It's not that this one wasn't important, but basically this one and this one together make this one. And so instead of having more numbers in our equation than we need, we say, oh, we just went ahead and combined them. So we're only putting one and we put it on the side with x. And that's just sort of like the way we do that, okay? All right, any questions so far on separating or integrating?
So at the very end, it should always be, we should always just put a c on the sides where we have the x.
Yeah.
Okay.
Now, in this particular case, okay, we can actually simplify this a little bit more. And the reason why I'm gonna have us simplify it is because that'll help us maybe understand the second part of today's lesson a little bit better. But one of the big things that kind of happens when you get to differential equations is people care a whole lot less about simplifying, because all of the work you do up until then is already so much that we're like, we don't really need you to solve for y. It's fine, okay? But for this particular case, we're gonna go to what we call an explicit solution, okay? So at this stage, we have right here our implicit solution, okay? So if your instructor says, find an implicit solution, you can stop as soon as you're done integrating. That's fine. Every professor is a little bit different for differential equations. There's always some who really want you to find the explicit. There's some who want you to find the implicit, and then there's some in between. And so that's just going to be a very, very much a personal choice based off of your instructor. So if and when you get there, just make sure that you ask to clarify what kind of solutions they're looking for, okay? But like I said, we're going to go ahead and find our explicit solution, meaning we're going to get y all by itself. So to do that, I'm going to go ahead and put e to the power of both sides, meaning I'm going to have e to the natural log of y. And that's going to equal e to the whole other side, natural log of 1 plus x plus c. Okay. Now, on the left-hand side, what happens after I've raised both sides to that power?
Y.
Exactly. So I'm going to end up with, now will I still have the absolute value or will I not?
No.
No,
Why not?
because the absolute value was only important in the ln solution.
Yeah, because you just can't take the ln of a negative value.
Okay. Now, what does that mean in terms of solutions? So we have a y here. Does that mean we can put any number in for y?
Actually, no. The absolute value is important.
Would it be like if you're taking a square root and it would be plus or minus?
Okay, so that is definitely something that we want to consider, right? Like, I agree that e can be raised to any power, like positive or negative is fine. But if we think about what's happening here, okay, those mean that I'm going to be getting only certain values that I can plug in for y, which is going to impact the numbers that kind of come out, okay? So for right now, we're going to keep these absolute value bars here. Now, when we look at the other side, though, okay, we have two things in the exponent. We have the natural log of 1 plus x, but we also have a plus c. What we're going to do is we're going to split this into two separate statements. So we're going to have e to the ln of 1 plus x, and then times e to the c, right? Because that's how exponents work. If I had x squared times x to the third, that would give me x to the 2 plus 3, right? We know how to work in this direction really well, but what's going to be important for us is knowing that how to unpack that, right? If you have two exponents that are added to each other, they really came from the base to that first exponent times the base to the second exponent. The nice thing about that, and the reason why we do that, is because e to the c, e is a number, c is a number. So everything in that orange is a number. And so what we usually do is we take that whole thing in the orange and we just call it a constant. We don't even write the e to the c, we just write it as a constant. And then what happens with the e to the natural log of 1 plus x, those again undo each other and we have 1 plus x.
Professor, the e to the c, like it was plus c up there, but is it times c in the bottom?
Yep.
Professor?
I just
Professor?
hold on one second. I just want to clarify. It's for this reason. That's why it becomes a multiplication. Does that make sense?
Yeah.
Yeah. Can I still ask a question?
Yeah.
So for that explicit solution, c is like on the outside of the absolute value bars. So just because it looks like parentheses to me, would we be able to distribute that c into the absolute value bars, or is that like just a no-go?
It's not that it's a no-go, but nobody does that. Yeah.
I was just curious because, like, I mean, because it looks like you could distribute it, but that would just mean the same thing essentially.
Right, exactly. And at the end of the day, what you tend to find as you go into higher math is like mathematicians tend to be really lazy about like writing extra things. Like they don't even want to write e to the c, they just call it c. So
Yeah. Okay. Okay. Thank you.
you're welcome. All right. So what we have, we separated, we integrated. After we integrate, we technically already have our solution, right? We have our implicit solution. We are going to be using this version of the explicit solution a little bit in 7.6, which is why I wanted to give that to us. But the rest of the examples we're going to look at are just going to be, we'll stop after the implicit solution, okay? All right, so let's take a look at example number 2. All right, so we've got dy dx equals negative x over y. This right here is our differential equation, okay? So what is all this other stuff that we have here? This is something called initial conditions, okay? And what initial conditions do is they help us find our answer not just with any old C, but a very specific C. This gives us, we will be able to get a number, gives us a number for C. Okay, so at the end of this problem, we're going to have our implicit solution, but we're also going to have a number in for C. So we will not have any C's in the end of our answer, okay? So help me out. How do I separate?
Multiply both sides by y dx.
Multiply both sides by y dx. All right, that's going to give me y dx. Well, y dy equals negative x dx. Okay. It was a very short step, but this is our separate. Okay. As soon as you've got the x dx and the y dy, you've separated. Now we're going to integrate. So I'm going to integrate y dy, and I'm going to integrate x dx with the negative sign in the front, okay? And this is going to give me y squared over 2 equals negative x squared over 2 plus c. So separate, integrate. No weird algebra things happening here with exponents, okay? So very straightforward, just the power rule. Now, what this gives us here, what color did I use? Implicit solution. This is our implicit solution. Okay. More specifically, it is a implicit general solution. General because we still have a C. But since we have initial conditions, we can find a particular solution or a specific solution for this where we know an exact value for C. And the way we're going to do that is we're going to take our initial conditions. They gave us an X value and a Y value. What X value did they give us?
4.
4. Okay, so 4 is an X value. That means negative 3 is our Y value. So we're going to take our implicit general solution, and everywhere we see a Y, we're going to put negative 3. Everywhere we see an X, we're going to put a 4. Now, the only thing we don't know is a C. That means that we can solve for C, get the number, okay? So on the left-hand side, we have 9 over 2. On the right-hand side, I have negative 16 over 2, and then plus C. I isolate my C value, so I'm going to add 16 halves to both sides. So I get C equals 9 halves plus 16 halves, which gives us a total of 25, right? 25 halves. What that means is in my implicit general solution, everywhere I see a C, I'm going to replace it with 25 over 2. Okay. To write my final answer, okay, I'm going to just write my equation again. Y squared over 2 equals negative x squared over 2 plus 25 over 2. And this right here is considered my particular solution. Okay, so it's not a general solution, it is a particular solution. You could multiply both sides by 2. You don't have to. Like, this is totally fine. But if it really bugs you, you can certainly multiply both sides by 2 and get rid of those halves. Okay.
Which one would be the solution general?
What's that?
Well, which one would be the solution general?
In general?
Because it says implicit versus solution general. Which one out of these will be the solution general?
No, that's implicit general solution.
Yeah, it's both.
Implicit solution general? I thought I said versus, like comparing two things. Okay.
That's not versus, it's an arrow to include the word general in the middle.
Does that make sense? Sorry, the volume is really low. I'm having a hard time hearing you.
Oh, it's because I thought it said implicit versus solution general. So I was like, what is solution general? But I guess it was just a mistake or a typo, maybe.
Yeah, it's just saying this is an implicit solution of a general form. It's a general solution because it has the plus C. Yeah, okay. Thank you folks for stepping in and helping clarify. I feel like sometimes, like, because I'm writing it, I'm like, oh yeah, well, this is what I meant, but I appreciate your different perspectives to help each other out. Okay. So let's move along. Let's take a look at example 3, okay? So let me give you guys a moment to go ahead and separate, for example 3. How would you separate this, okay? And by convention, we typically have the dy's on the left side and the dx's on the right-hand side. It's not wrong if you do it the other way, but I don't know that you'll find an answer key where the y's are on the left-hand side and the x's are on the right. So make sure that, like, it's usually we keep the dy's on that left-hand side, okay? So take a moment, try and separate example 3. Example 4 is there as well if you want to skip ahead to that one and go ahead and separate. All right. Anyone got a first step for number 3 to separate?
Divide both sides by dy and dx. After you have subtracted the one side, sorry.
After I subtracted the what?
The 4 plus x squared dy.
Okay, but we want to keep the dy's on the left-hand side.
I subtracted 1 plus y squared dx.
Yeah, again, by convention, we typically move the dx. We don't really move the dy, okay? So we'll have 4 plus x squared dy equals negative 1 plus y squared dx. Now, what do we want to divide by?
Divide by
Two
1
parentheses.
plus y squared and 4 plus to each side.
Mhm. All right, that's going to get rid of these. That's going to get rid of these. Okay. And what we end up with is dy over negative 1 plus y squared equals dx over 4 plus x squared. Okay. So it's not wrong if you move the dy, but again, we typically, like 99% of the time, we keep that dy on the left-hand side. We don't move it, okay? The other convention that we tend to do is if there are any minus signs or constants, we typically leave them on the side with dx, okay? Meaning I'm going to divide both sides by -1 and keep the dx negative, but keep the dy positive. So that'll give me 1 over 1 plus y squared dy on the left-hand side and negative 1 over 4 plus x squared dx on the left-hand side, or on the right-hand side, okay? You could have done this without dividing by a negative sign in the beginning and still gotten the minus sign to stay on the x side, okay? Now, we've separated. So all of this is our separate. And so now what we need to do is go ahead and integrate, okay? So when we integrate 1 over 1 plus y squared dy, all right? And then we also have to integrate the other side. What do we get on the left-hand side when we integrate?
Extension.
Yeah, we get arctan, okay? So I know we did a lot of work with trig subs, but we also want to recognize when we see the inverse tan one, right? It just saves us a little bit of work instead of having to do the whole sub. So this goes to the arctan of y. The other side, also an arctan situation, but we need a coefficient in front of it. What's that coefficient?
2.
2.
I'll take a 1/2. How's the 1/2 sound?
Yeah.
Yeah, okay. So we have our minus, because we had the minus sign in our starting one. So we had the minus here, so it continues. And then because a is 2, I need 1 over a arctan of x over a. Okay. Then we put our plus c on the right-hand side. Okay. This, because I had no initial conditions, is totally fine. If I don't have initial conditions, I can only find a general solution. Okay. And I can also leave this in its implicit form, meaning I don't have to solve for y. I don't have to tangent both sides to get that y out of there. Okay.
Professor,
Yes.
can you explain again why here you don't have to do that, but on number 1 we did separate for y?
I'm not sure I understand your question.
He's asking about the explicit solution thing.
Okay, so I know like we're used to solving for y. We don't have to solve for y. This is fine. The reason why I wanted us to solve for y in example 1 is because that's going to lead into what our second part of our lesson is.
Oh, okay, thank you.
Okay, cool. All right, let's take a look at example 4 and example 5, okay? So when we take a look at example number 4, I see that there are two terms and that one of them has the dy and the other one has the dx. So by convention, I'm just going to move the term with the dx to the right-hand side, but I'm going to keep the dy on the left-hand side. So we'll get x squared dy equals cosecant 2y dx. Okay. I'm going to divide the x squared, and I'm going to divide by that cosecant 2y. I will end up with 1 or dy over dy over cosecant 2y equals dx over x squared. Okay. Now, I didn't write this out as much as I did the previous ones. Are there any questions about how I got to this step? Okay. So before we integrate, it's always nice to have things in a form that is easy for us to integrate. Like, we know we're going to be integrating. So we want to set it up for ourselves so that we can actually see what we're going to be integrating. So for example, on the right-hand side, I would write this as the integral of x to the negative 2 dx, because I want to remind myself I have to use the power rule. What might be a good way to rewrite the left-hand side?
Sine 2y.
Yeah, okay, so this goes back to a pretty fundamental trig identity that 1 over cosecant is actually the same thing as sine of whatever you're cosecanting. Okay. So before you panic and you're like, I don't know what the integral of 1 over cosecant is, just see if there's a way to simplify it, okay? And now I think it's a little bit more clear. On the right-hand side, we're going to use power rule, but on the left-hand side, what rule do we need to use? When we integrate.
Power rule.
Chain.
What's the version of chain for integration? Because chain is for derivatives.
Oh, well, when you bring that down, well, I know that when you integrate it, you're going to get the negative cosine, but then you got to do the fraction for that too. So it would be a 1/2.
Yeah, it is going to be a 1/2. That's called u sub, right?
Oh, okay. Yeah, I was like, what?
Yeah, it's our most straightforward u sub, and so we'll get negative 1/2 cosine of 2y equals, and on the right-hand side, I will have negative x to the negative 1 plus c. And I would say the only rewriting that you might want to do is just to say that you have negative 1 over x plus c, but really not a lot of difference between the first answer and the second answer. Okay. Any questions on example 4?
I have a question.
Yes, Gabby, what's up?
So can you change the -1/x to the negative natural log of x?
Why would you do that?
Oh, I don't know. It's just isn't like I don't know.
Negative 1/x is not equal to the natural log of x. Like those are not the same thing.
Okay.
Okay.
Mm-hmm.
So when we're integrating, we want to make sure like we're aware of what we're doing, right? So like 1/x, how do I get to natural log of x? I would actually have to integrate. So I think you're confusing that with integrating.
Oh, yeah, I see.
Yeah.
I think I just got confused.
You know that so well though, right? Because that is definitely an integral that pops up a lot is you get like a 1/x, and that's not the power rule, right? That is the natural log, but they're not equivalent. They're just an integral of each other.
Okay, I see. Yeah, I think I just got confused.
Yeah. I think we're all feeling maybe a little tired. I feel like first day after a test is always hard. Okay, let's take a look at example number 5. Okay, so let me give you folks a couple minutes to separate and then integrate. I will tell you there are no really weird integral rules here. Okay, we can get away with a simple U sub to get to our answer when we're ready to integrate. Okay, so don't overthink this one. Separate, integrate, and know that U sub is the only integration technique you'll need here. All right, how does that look in terms of separating? Are folks getting something similar to that?
Yes.
Yes, okay, good. Got that, okay, cool. So now I think it's actually particularly important, especially for that left-hand side, to rewrite it in a way that is easy to integrate. Meaning I don't want to write 1/e to the y. I'm actually going to write this as e
to negative y.
y. Exactly, okay? That shows me I'm going to use a very simple U sub on this left-hand side when I integrate. So I'm going to integrate this side, and when I integrate the other side, right? Now I know I told you folks, all right, we're going to use U sub, but what is the U that we're going to have for this?
U sub. U1
Sine.
cosine.
Is it going to be sine? Okay, I hear a couple
cosine.
signs. Yeah. We want to make sure that, because if we had it as cosine, we would have like du, or if we had it as sine, we would have like du squared, and that's not really going to work for us. So we've got a cosine x, du equals positive or negative?
Negative.
Negative sine x dx. all right? Which means that when I replace this, I'm going to have a negative sign in the front. So on the left-hand side, I will get negative e to the negative y with a very straightforward u sub, right? Just changing the sign. And then just to show us this one step, I have negative the integral of 1 over u squared du, which might be easier if we write it as negative the integral of u to the negative 2 du, so that we don't get distracted by u in the denominator and think natural log, but rather we want to use the power rule here. So we get negative e to the negative y equals negative. This is going to give me negative u to the negative 1 plus c. And as a final answer, we just want to put back in our u to be cosine x. So we'll get negative e to the negative y equals 1 over cosine x plus c. All right. Any questions on example 5? All right. Well, we've got 2 other examples to go through. Okay, so we've got example 6 and we've got example 7. And I think of these kind of like as a little bit of a step up. Okay, they're going to be a little bit of a step up for a few reasons. It's going to involve a little bit more algebra, and it might have more complicated techniques that we need to use when we integrate. Okay. So let's take a look at example number 6. Now, in most of the other examples, we've seen dy and dx separate. I think one of them we saw dy over dx, but remember we can always multiply that dx to get it out of the denominator. And so if I think about that as a first step, I'm going to end up with e to the 2y minus y cosine x ey equals e to the y sine 2x dx. Now I am going to divide the e to the y, and I'm going to divide the cosine. So this is going to give me e to the 2y minus y over e to the y. And on the other side, sine 2x over cosine x dx. Okay. Let's actually start with the right-hand side here. So a lot of us have gotten quite savvy at thinking about trig subs, which I really appreciate. So what can I replace sine 2x with?
Cosine x, cosine x.
Exactly, 2 sine x cosine x. That double angle formula comes in so handy, okay? So I've replaced it, which allows me to reduce the cosines and the cosines, which means what I'm actually taking the integral of is 2 sine x dx. And that we can all do, okay? So this one I think was a little bit trickier just because we needed to do a trig identity. All right. And I think what makes the left-hand side a little bit trickier is simply algebra. All right. I see my fraction, but I'm actually going to split it into 2 different fractions. And so when I do that, I'm going to get e to the 2y over e to the y minus y over e to the y. And all of this is times. What does this first term reduce to?
E to the y?
E to the y, brilliant. How'd you get that?
It's just minus the exponent.
Yeah, exactly. 2y minus y gives you 1y. Okay, now e to the y, I'm like, I know how to take the integral of that. We're going to be good. But the second term I'm actually going to rewrite it as minus y e to the negative y. Okay. Because there's nothing I can really simplify. Like I certainly can't cancel out the y's, but I'm going to have to write it as a product of two terms, y times the denominator, e to the negative y. Okay. Now, this we know the integral of. E to the y, we're good. Integral of 2 sine x, we're good. How do we integrate y e to the negative y?
Parts. Integral by part.
Yeah, this we're going to need integration by parts. Okay. We're not going to finish this question, all right? What I wanted to do is set us up to see like all the different techniques, like all that stuff that you invested in chapter 9. If you're going to differential equations, you will definitely reap the rewards of having learned it really well the first time. Okay, so if you're feeling confident with your trig subs and your integration by parts and things like that, it definitely pays off. You might not see as much of that in Calc 3, but if you go to differential equations, then you'll see a lot more of these techniques come back, okay? All right, let's take a look at this example number 7, okay? So for example number 7, at first it might seem like it's not separable, but keep in mind I can take like x squared minus 4 as a whole term. I can treat that as a whole thing. So I'm going to multiply the dx to both sides. That'll give me dy equals y squared minus 4 dx. And then I'm going to divide that y squared minus 4 to the other side. So dy over y squared minus 4 equals dx. Now, when I integrate dx, what do I get?
X.
Yeah. So this side, really straightforward, right? When we integrate 1 over y squared minus 4 dy, what techniques might come in handy?
Second.
Yeah, which one?
Partial fractions.
Okay. So I heard, let's stick with the trig sub for a moment. Which trig sub should we use in this case?
Second.
Secant.
Yeah, exactly. We could let y equals 2 secant theta, and dy would equal 2 secant theta tangent theta d theta. Okay, so that's one option. The other option, and whoever said it, I didn't mean to cut you off, you were not less important, okay? But partial fractions is definitely a technique we could also use here. I forgot how to spell fractions for a moment. Partial fractions. Okay, so partial fractions is another technique that we could use. We could find it being like 1 over y minus 2 times y plus 2 is going to equal a over one of those denominators. My handwriting is atrocious today. Plus b over y plus 2, and then you could solve for a and solve for b. And I think that this one is actually pretty straightforward to solve for, so it's really up to you whether you want to use the trig sub or whether you want to use the partial fraction, okay? But again, we're not going to finish this problem per se. I just wanted to kind of prime you for when all these things that you learned at the beginning are going to come up again. Okay, that's really the bigger point. And if you felt like that first exam went really well, if you are going to take differential equations, I would really encourage you to just brush up on these again before the start of your semester for differential equations. And I think you're going to find yourself leaps and bounds over a lot of the other students in the class, especially if they didn't learn it so well the first time, or if they didn't take the time to review. That's when it tends to be a little bit harder, okay? So, are there any questions about the about this section, differential equations, just like an overview? Okay. Well, we are going to stop the video right here.